Okay, today we're going to be talking about the intermediate value theorem. And this is a really simple concept that looks a little confusing when written in math terms. So we'll get right into it, and then I'll explain it with like graphs, and then it'll look super simple and you'll get it. So the intermediate value theorem states that when a function f of x is continuous, and we already know what determines continuity, as we learned from the last video. If a function is continuous on some closed interval from a to b, and these square brackets as opposed to the parentheses denote a closed interval, which means the interval includes the endpoints. So this just means for every number between a and b, including a and b. So if f of x is continuous for every value of x between and including a and b, when f of a does not equal f of b. So these are the two like qualifications for a function to agree to the intermediate value theorem. It has to be continuous on an interval from a to b, and the two endpoints of the function on that interval have to be different. So when a function is continuous on a to b, and when f of a does not equal f of b, there exists a value of c where f of c equals k for all of k is in between f of a and f of b. So what that means is, when you're looking at a graph, right, you have
Oh.
Yeah.
Are you recording?
Yeah.
Okay. When you're done, when you're done.
Okay. Okay, so that means for a function at a to b, and let's say this right here is f of a, and this up here is f of b, right? So for a function to, and we can make up anything here, and here, okay. So what this means is if a function has a point here and a point here and is continuous everywhere from a to b, that means every value from f of a to f of b, every value in here is accounted for between a and b. So I like to draw this little box. And to see this, that means you cannot draw any line, any type of function that doesn't connect these two dots and hit every value on here, right? So to further explain this, let's try and do it. Let's try and prove the intermediate value wrong. So let's say you're trying to get from here to here, but we never want to cross this line. So, okay, so we got to go up to get to this point. So we go up. Oh, we don't want to cross this line, so let's go back down. But then eventually we're always going to have to go up through this line to get to here. That's all the intermediate value states, is that for every y value between the starting and end points on an interval, every y value is accounted for. Like there's no way the function can get from here to here without crossing every single line. Like it also crosses there, and it also crosses here. It crosses every line we can draw to get to that point. Great. So, some questions you'll be asked is, this is all coming from the notes. So, given f of x equals 1 over x minus 2, 1 over x minus 2, and k equals 1/4 on the interval 2.5 to 7. So we're given this information, and we have to state if the intermediate value holds for this function and value of k, and then if it does, we have to find where this function equals 1/4. So first, the way we do this is we check both the endpoints. So we plug in f of 2.5, that's our starting point. So that's going to be 1 over 2.5 minus 2. So that's 1 over 1/2, which is just 2. So that means the leftmost endpoint on our graph that we draw is at y equals 2, right? And so we find the rightmost endpoint. And that's 7, that'll be 1 over 7 minus 2 equals 1/5. So that means when on this interval 2.5 to 7, every value between 2 and 1/5 is accounted for. I'll draw this graph again just to make sure we understand. So if we're starting at 2.5 and going to 7, and we'll say this is 2, the function hits 2 up here, and then it also hits 1/5 down here. So we know by the intermediate value theorem, if this is continuous on this interval, which it is, every value from here to here is guaranteed to be accounted for on this interval. So the reason why we check the endpoints is to decide if this is accounted for by the intermediate value theorem. And it is, because 1/4 is between 2 and 1/5. So there's no line that we can draw from 2 to 1/5 where that 1/4 is not accounted for. So right here we know that the intermediate value theorem holds because this 1/4 is between 2 and 1/5. And now we are asked to find where it equals 1/4. Like we saw, there's some c where f of c equals k. So to find out where, or the value of c, all we need to do is set these equal to each other. So we have to find where the function equals 1/4. So we have 1 over x minus 2 equals 1 over 4. And we can do cross multiply this to the other side, multiply this to get 4 equals x minus 2, and then x equals 6. So when x equals 6, which to check is definitely in between this, on this interval, when x equals 6, that means f of x equals 1/4. So that's how we decide that the intermediate value holds, by finding these two values and then saying, oh, okay, this 1/4 is between these two. So that's how we know that we can use the intermediate value theorem, and then we just set these equal to each other and then solve for x. Okay, and another one that I like is use the intermediate value theorem. So use the intermediate value theorem to prove, here I'll just, okay, that all spheres, is that what it is? Okay, yeah, that for all spheres with radii between 5 centimeters and 8 centimeters, there is a sphere with volume 1500 centimeters cubed. Okay, so use the intermediate value theorem to prove that for all spheres with radii between 5 and 8 centimeters, there's a sphere with volume of 1500 centimeters cubed. So the way we start this is we find the volume of a sphere at 5 centimeters with a radius of 5 centimeters and the volume of a sphere with radius of 8 centimeters. And then if the volume at 5 is less than 1500 and the volume at 8 is greater than 1500, that means there's some sphere with a radius in between these lengths that makes the volume of that sphere equal to 1500 centimeters cubed. So we'll do the same thing we did with the previous one, where we find the function value at the endpoints. So we know the volume at 5 centimeters is equal to, and if you don't remember, the volume of a sphere is going to be 4/3 pi r cubed. So at 5 centimeters, it'll be 4/3 pi times 5 cubed. And we'll have to use a calculator for this one. All right, and that gives us 523.6 centimeters cubed. And so now we have to find the volume at 8 centimeters when the radius is 8 centimeters. 8 centimeters is, again, 4/3 pi r cubed. So it's 4/3 pi times 8 cubed. And that'll give us 2,144.7 centimeters cubed. So if we look at these numbers, that means between spheres with a radius between 5 centimeters and 8 centimeters, there's going to be a sphere with a volume of every point in between these. And since this asks for 1500, and that's between 523 and 2100, we know that there's a sphere with radius somewhere between 5 and 8 centimeters that makes the volume of that sphere equal to 1500. And so to find the radius of that sphere, we do the same thing we just did with the last one. We set the function value equal to this. So we set 4/3 pi r cubed equal to 1500, right? And then we can just solve for r, because that'll give us the radius of the sphere with a volume of 1500. So first we can multiply by 3/4 to both sides to get pi r cubed is equal to 1,125, I think. Yeah, so 1,125. And now we can divide by pi, and I'm not even going to try and do that in my head. So 358.1. And now we can just take the cube root of this, raise it to the 1/3, and then we get r is equal to 7.10. So what this 7.10 means is when the radius of a sphere is 7.10, that means the volume is going to be 1500 centimeters cubed. And we solved that by looking at the values at the endpoints. We always have to check the endpoints first, and then see if this value is in between these two function values at the endpoints. And if it is, that means the intermediate value holds, and that we can set the function value set the function equal to that value, and then solve for our variable, and that gives us our answer. So pretty simple, but may look confusing when it's all like written in math terms. But all it's saying is that you can't draw a line from here to here without crossing every line in between.